Welcome back to ECE 220. We are using differential equations in the application area of electric circuits. That's Chapter 7, and we're starting at the beginning, which is first order differential equations, RL and RC circuits. You need to be reading up on that. If you're in Group A, your section, you will be reporting to lab number 3. A couple sections have already done that. We have Thursdays and Fridays labs for lab 3 the rest of this week. Group B, your pre-lab for lab 3 is due Saturday, and your lab is actually next Tuesday for lab number 3. Homework 9 is now available, and it's due next Tuesday. That is dealing with, remind me what that's dealing with. Mutual inductance, isn't it? Homework 9, that's on mutual inductance. Group A, your lab number 3 report is due next Wednesday, so now we're looking a week ahead. A week from tomorrow, we will not have class here, and we will not have class the next Friday. So after exam 3, I'll give you a day to recover. Okay? Hopefully you won't be feeling beat up after exam number 3, and you won't need that day to recover, but you can use it to catch up. All your other stuff is going to be due. If you have something to turn in on various days, the fact that we are not meeting physically in class here does not excuse or change those dates. Meaning, Group A, your pre-lab number 4 is due on homecoming, Saturday. You can work ahead. You're going to have a day to do it extra on Friday the 1st. But exam number 3 is 2 weeks from today. We just keep sequencing through these exams. But we don't want to forget the labs, correct? What happens if you don't turn in a lab? You get 0 on the whole semester's worth of points, so don't do that. Even if it's late, submit it. Make sure you're sticking with or keeping up with the labs. The previous instructors have learned that if they don't make that big cost associated with the lab, some students will neglect some labs, and we don't want you to do that. So that's the reason for that high penalty, so to speak, or that cost associated with the labs. Today what I want to do is continue with our discussion of first order circuits, RL and RC, and most of the day, if not all of today, we'll be still dealing with the natural response of those systems. But first, let's just get a better understanding of when is a circuit first order, or can you now look at a circuit and tell me, oh, that's third order, oh, that's second order. That's what we'll do first. Then we will look at natural responses again. Now for RC circuits, we'll just quickly go through, it's a key word I hope, but we'll summarize working through RC circuits. If you're following along in the book, that's sections 1 and 2 in Chapter 7. That's dealing with natural responses. Then we will expand on that. We've just looked at a circuit that contains one inductor and one resistor, or one resistor and one capacitor. What if we have other resistors floating around or other capacitors? Can we solve for other circuit quantities? And if you want additional examples, those are in examples 1 and 3 of Chapter 7. Then we'll get into trapped energy. And this is kind of fun. I guess it's all relative, what we consider fun. But you can, if these elements are indeed ideal and they don't have any parasitic resistance, then you can actually have current circling in those parallel inductors, or you could have voltage across those capacitors. And those capacitors are actually in series. Do you see that? You've drawn them, make them look like they're in parallel, but they're not in parallel, are they? They don't have two nodes. Their two nodes at each end are not shared, but their common node is common. That's what puts them in series. You can now have a series connection of capacitors maintaining charge when the other two extremes of their terminals have zero voltage across them. That's trapped energy. We're not going to let it out. We're going to keep it trapped, or it will be trapped, and we'll work through some examples. And here are some that you can work in addition to what we talk about today. When is a circuit first order? Now we get to exercise a little bit. You get to at least open up your hand and show me one of three digits. 1, 2, or 3. Is this circuit first order, second order, or third order? And what determines order? Maybe I'll give you a little bit of a hint. What determines the order of a circuit? Generally, up until the last little bit, before we started talking about inductors and capacitors, everything was happening instantaneously, wasn't it? Our resistive circuits were just immediately showing currents and voltages. There was no energy storage to give us some delay or exponential behavior in our circuits. When we have energy storage devices, that's when we have order. And generically, if we have 4 energy storage devices, 2 inductors and 2 capacitors, let's say, generically that would be a fourth order system. I now ask you, what's the order of this circuit? At the count of 3, I want you to show me your fingers. Show me your answer. Okay? 1, 2, 3. And I think I misled you, didn't I? Everybody's saying 2 because there's 2 energy storage devices. But I tried to kind of hint earlier, but if you connect those together, you can now, that's common, right? That common node. Now you have 2 capacitors that are an equivalent single capacitor. Those 2 capacitors are in series, so in fact, the order here is 1. So that's not a generic circuit. That's kind of a special circuit. Those capacitors can be combined into an equivalent capacitor. Now we could say, oh, what is C equivalent or C effective? I may use it interchangeably. Let me say, what's the effective capacitor that resistor sees? It's this series combination of C sub 1 and C sub 2. And how do capacitors combine in series? Yes, capacitors are the dual of our inductors, aren't they? Inductors combine like resistors, so now in series with capacitors, the effective capacitor would be C1, C2 over C1 plus C2. And here, let me just make it clear that that's what I'm saying. C1 and C2 are in series. All right, maybe we miss one. Let's see what happens with 2. Have a few swings at this since we're in the World Series. All right. What's the order of this circuit? 1, 2, or 3? We have 3 passive elements, R, L, and C. What's the order of this circuit? One, 2, 3. It is second order. We have two energy storage devices, and they can't be combined into an effective or an equivalent single energy storage device. We now have one inductor in series with one capacitor. That's now, we have two energy storage elements. Three. What's the order of 3? I'm trying to make sure that we can engage all of our digits if necessary. All right, at the count of 3, are we ready? 1, 2, 3. We're kind of split, but we're all even, it looks like. We're kind of split between 2 and 4. But now, kind of step back and look at this. How many energy storage elements do we have? 4, but we can actually combine some of these because they're in series. If we redraw this, let's say that we now want to redraw this circuit. I can move these around. If I want to try to model what this circuit is doing, I could now say, oh, I'm going to just put all of those resistors together. That's now R1. They're in series, R2, R3, and R4. I can do the same with the capacitors, C1 and C2, and the inductors. Now do you want to change your answer? So now we have many different effective elements. We have R effective, which is the sum of those 4 resistors. We have L effective. What's that? Expression-wise. Series combination of inductors, that's L1 plus L2, and now we have this. What's C effective? Those are in series. That's now C1, C2 over C1 plus C2. The answer is that bad boy is second order. Even though it has 4 energy storage devices, effectively you can combine the inductors and capacitors into one effective element each. And you now just have 2 energy storage net in that circuit. Circuit 4. What's the order of this circuit? 1, 2, 3, or 4? We ready? 1, 2, 3. So now on this one, could we combine those into an effective inductor? Those are in parallel. They share 2 nodes, and in this case, the effective energy storage is just one element with L effective. This is now first order. L1 times L2 over L1 plus L2. If you combined all of those into a single effective inductor, you would now have an RL circuit, which is what we will be analyzing shortly, or an RC circuit. One more. What's the order of this circuit? One through 5. Ready to answer? All right, we'll answer at the count of 3. 1, 2, 3. It's actually all, isn't it? It's 5. There's no way of combining, no effective L's or C's. Aren't there 5? 1, 2, 3, 4, 5. There's 5 energy storage elements. There's no way of combining. None of those L's and C's can be in parallel or series, in pairs or triplets or however. They just is not happening. So this is now, we have no effective L's or C's. Now maybe you have a feel for what we are talking about. Oh, and this, should this be on the final? Fifth order differential equation. Is it linear? Is it? Pardon? So it is a linear circuit. We're assuming all of our L's and C's are our ideal passive devices. They are not going to be any functional variation other than what we know them to be, Eli and ice. This would be a linear circuit. It would be fifth order. You could apply whatever strategies you want, but you'll get that in 320. Okay? 320A, you'll be able to do this in your sleep. Okay? I'm not teaching 320 next semester. Sorry. So, I don't know what's happening next semester. That's too far away. Usually changes in about a week's time. Is my name on that class? It is? Am I? What? Oh, man. Okay, so I'll have to talk to the person that assigns classes. Oh. All right, we'll see what's happening with that. Natural response of an RC circuit. We did natural response of RL circuits. Let's now look at RC circuits. And do you understand why we have the switch in this circuit as sketched? That switch is there to try to energize the capacitor, create some initial condition on that capacitor so that when we swing that switch at t equals 0 to the other side, we now have a RC circuit, but that capacitor now has some energy associated with it that will then dissipate through that resistor. Again, this is supposed to be a summary, so let's kind of step through this quickly if possible. What is the initial capacitor voltage? V sub C of 0 minus. Oh, and why am I worried about the capacitor voltage and not the current? Current's 0, isn't it? What did we say about different variables. The state variables, do you remember what we talked about yesterday? What's the state variable associated with a capacitor? Current or voltage? Remember ice? Which one's the last one? E, which is the voltage. So we concentrate on voltage. That's our state variable with capacitors. If it was an inductor, we would be keeping track of the current, because those variables, the voltage on a capacitor and the current on an inductor, remain continuous. So whatever this voltage is on the capacitor at time 0 minus, it's still that same value at 0 plus, just on the other side of 0. What is the initial capacitor voltage? Well, for t less than 0, we can redraw that circuit. We can just say, well, the switch has been in place since minus infinity up to 0, and we'll just, if you wanted to think about that a little bit more carefully, you would say, oh, from minus infinity up to the edge of 0, 0 minus, coming in from the left. Time now, this is what V sub c of t looks like, and for the majority of that time interval, what happens? Well, that capacitor, its transient disappears, and what happens to the capacitor? After the transients in this circuit, what's that capacitor behaving like? Capacitor acts like an open or a short. With DC sources, this capacitor acts like it charges up, and there's no current flowing, is there? So now a capacitor acts like an open circuit to DC sources. And that now allows us to redraw that and say, oh, we actually have this circuit. And this one we can write KVL if we want. We could say, oh, here's a current I. KVL says we have minus V sub G plus R sub G I plus V sub C. And let's just say that we're close enough to the origin that it's in its steady state position. The current in that open circuit is nothing, so I hope you can see that that capacitor is now charged up to the original voltage source, DC source, that we had it connected to before time t equals 0. The initial condition, the initial voltage on that capacitor is now V sub G. V sub C of 0 minus is V sub G. And now we actually know what V sub C at 0 plus is, because the capacitor voltage is continuous. It's going to be V sub G. After time 0, now the switch goes to the right, and now we simply have this capacitor and resistor in parallel. How did we analyze that? Or how would we analyze that? I guess we did analyze it yesterday. What equation did we write? KCL or KVL? We were interested in capacitor voltage, which is this voltage right here. And we can write a nice equation that contains the capacitor voltage if we focus on writing a KCL for this circuit, and that says then that we have the sum of the currents out of that top node sum to 0. Or we now know that we have RC dV sub C dt equaling minus V sub C. And if we define our time constant to be RC, then we have tau dv sub c dt is equal to minus v sub c. And that we solved last time, at least for the inductor case. It's the same structure now. This is now v sub c of t is equal to v sub c of 0 plus e to the minus t over the time constant tau. And I tried to communicate that we did know v sub c of 0 plus. What's the rationale for saying that we know v sub c of 0 plus? What do we know about the capacitor voltage? It's continuous. So now we do know v sub c of 0 plus, the capacitor voltage remains continuous. Thus, we know that we can say, okay, v sub c of 0 minus is equal to v sub c of 0 plus, which we solved just a minute ago to be v sub g. Therefore, the solution for t greater than or equal to 0 is now v sub g e to the minus t over tau t greater than or equal to 0 for tau equal to RC. That's our quick summary of first order circuits for RC and RL. We did RL last time, now you've seen it for RC. What if somebody gave us this circuit? Suppose we had a different circuit with more resistors attached in a weird way. It's not just one resistor. And now they're telling us what the initial voltage is. We don't need to worry about all these switching things. We just said it happened, and now we have this capacitor charged to 10 volts at time 0. And now, can you solve this based on what we've just talked about with these RL and RC circuits? Is it possible now to use that capability to analyze this circuit based on that and what you've acquired up through the semester? Now we have three different, and so I might ask for what's I sub 0, what's V sub 0, what's the energy consumed or dissipated in R sub 3, etc. We should be able to do that. And the way that we will do that is sort of like what you did when you were collapsing resistive networks down and then just finding what was happening with a particular source and one effective resistor. We can collapse all of those resistors down into an effective resistor, and then that effective resistor will be in parallel with that capacitor, just like the example we just worked. So, can we use the earlier solution to find other variables, in particular powers, energies, V sub 0? I hope that I've convinced you that the answer is yes. Now we can collapse what that circuit was into this equivalent circuit, and we know how to analyze that one. We want to now convert this one into this. That means we need to find an R. a single R, or an effective R. Where? Across the terminals of your capacitor. Your now terminals of the capacitor, or let's say terminal A and terminal B, you want to go, okay, what's the Thevenin resistance between those two terminals? What's the resistance between terminals A, B, where A and B are on either side of the capacitors, and now we're looking into that circuit from the left to the right, and we want to know what's the effective resistance seen by that capacitor. If we can find that, then we can just write the circuit as this and analyze it with that effective resistor. And we can then find the voltage of that capacitor. That's going to require us to find R effective. And what is R effective in this case? I'm now wanting to look to the right from A and B. I now want to see what's the effective resistance that that capacitor sees. Do you see that you could simplify it if you just combined R2 and R3 as parallel resistors? So let's now combine those two. R2 and R3 are in parallel. Now that combination is in series with R1. And that series combination of R1 with that parallel combination now gives us the effective resistance seen at terminals AB. Or R effective is now, what were the labels? R1 plus R2 in parallel with R sub 3. And numerically, this was 0.4. R2 was 2 in parallel with 8. That's now 2 times 8, or 16, divided by 2 plus 8, or 10. That's 1.6. Or R effective is now 2 ohms. If we now know that this is 2 ohms and this C is our 1 farad, what's our time constant? For an RC circuit, what's tau? RC. So that's R effective times C, or that's 2 times 1, or this is now 2 seconds. That's a pretty large time constant. What's infinity? How long would we have to wait before we reached infinity in this circuit? 5 of those 2's, or 10 seconds. So that's how long we would have to wait before everything was done or finished. If we now know tau, we now were told the initial condition on the capacitor's voltage. Can you now write down an equation for V sub C of t? Here is now the V sub C of t in this circuit. V sub C of t is now V sub C of 0 plus, which was 10, e to the minus t over tau, and tau was 2. Or this is now 10 e to the minus 0.5 t for t greater than or equal to 0. Now, how do we use that? Now that we know the voltage across AB, terminals AB, how do we use that to find V sub 0 and I sub 0? What does that look like. We might, and that V sub 0, it's sure snuggled up to R sub 3, but it's exactly the same voltage across R sub 2, isn't it? That parallel combination of R2 and R3 experienced the same voltage drop, V sub 0. So now we could say, oh, there's an effective resistor there in series with R1. Hint, hint. Do you see what I'm begging you to see? V sub 0 you can find by a voltage divider. You can now just divide V sub C across those two combinations of resistors to find V sub 0 of T. So let's now do that. V sub 0 of T, well, let me just say a voltage divider, allows us now to say that V sub 0 of T is that parallel combination of R2 and R3, which was 1.6 over R1 plus that 1.6 times V sub C of T. Or, I didn't give myself enough room. That's now 1.6 over 2, or 0.8. 0.8 times V sub C, and V sub C had a gain of 10, so this is now equal to 0, well, let me just, 1.6 over 2 times 10 e to the minus t over 2, or this is now 8. 0.8 times 10, 8 e to the minus 0.5 t greater than or equal to 0. Actually, let's say greater than or equal to 0 plus. Because right at 0, that voltage across that resistor could be discontinuous. We know that the capacitor voltage is continuous, but all the others we need to kind of compute or calculate. So this is now V sub 0 of T, 8 e to the minus 1/2 t. What's I sub 0? If we know V sub 0, can we compute I sub 0? That's Ohm's law. So we divide V sub 0 by 8 and we'll have I sub 0. I sub 0 now is now 8 divided by 8, or V sub 0 of T over 8 is equal to e to the minus 0.5 t for t greater than or equal to 0 plus. And now we might want to know or answer the question, what's the total energy dissipated in R sub 3? And I'm giving you kind of a roadmap. What's the power associated with R sub 3? How do we find the power? Instantaneous power. And I'm really giving you a lot of hints here by the appropriate scrolling of the screen. What's power? V times I. We have both right in front of us. We form their product. We can now find the instantaneous power for all time from 0 up to infinity experienced by R sub 3. How do we get the energy from power? Power is what? Energy per time. So if we integrate power, we can find the energy. Power is now V sub 0 of T times I sub 0 of t, which is now 8 e to the minus 0.5 t, e to the minus 0.5 t. How do those exponents combine? Those just add, so now we have 8 e to the minus t for t greater than or equal to 0 plus. And that's in units of watts. That's the instantaneous power. Energy, we said, was the integral of that. Now we just have to be able to integrate an exponential, which is one of the easier functions to integrate. We evaluated the upper limit. That vanishes. We now have minus 8 times e to the minus infinity minus e to the 0. We have a minus 1, or we now have 8 joules that R3 dissipates. That's the energy dissipated by R sub 3 for all positive time. How much energy was in the circuit to begin with? Well, we can find the energy in the capacitor at t equals 0 plus. This is going back. What's the energy in a capacitor? Do you remember the formula? Exam 3, you'll have to remember this. 1/2 C V sub C of 0 plus. And we have that information. We have the C, that was 1. We have the V sub C at 0 plus, that was 10, and we square it. We now need to divide 100 by 2. What in the world? R3 took 8 of the 50. What happened to the other? What happened to the rest of the energy? Is it magic? Now we know at time 0, we started with 50 joules in this circuit. R3 took 8 of those. R1 and R2 are going to take their share, aren't they? More of their share, or more of the share of 50 than R3 takes. I think I'm going to let you do that on your own. Can I? Where am I? What happened to the energy? And if I tell you the answer, you can check, right? Tonight, at home, or sometime. What did I compute? So the energy in R sub 2 was 32 joules. And now you can figure out what the energy in R1 was by elimination, but that was now 10 joules. That's how the energy is dissipated across those 3 different resistors. And you can compute that by finding voltage and then dividing by R or whatever and integrating that. Let's talk about trapped power. I want out. I want out. Where is this power trapped if it's wanting out? It's not getting out, is it? It's now circulating. We have... Now this is kind of a head scratcher, so let's think about this. We're now claiming that this current just circulates. Some residual current. Current circulates as t goes to infinity. And over here, there's just charge that remains on that series combination. But the two terminals to that resistor, it looks like there's no voltage dropped across that series combination of C1 and C2. So the charge remains on C1 and C sub 2. So let's look at that. An example. Suppose you're given the following combination. This is now energy trapped in capacitors, series combination. This series looks a little bit more instantly determined versus having them connected to a common, and then we have to realize that that's a connection and oh, they're in series. This one's spelled out for us. We now have V1 being a negative 2 volts and V2 being 10 volts at 0. And now we want to find the initial energy stored in the capacitors. We also want to answer some other questions. We want to find V1, V2, V, and I sub 0. We're inquisitive today. We want to find the energy stored in the capacitors at infinity. Is there still energy in those capacitors as time goes off to infinity? And find the energy absorbed by R and comment. So now you need to write a paragraph on your comment to what happened with that energy relative to R. Question A, find the initial energy stored in the capacitors. Do you have information enough to determine that? We know the formula for energy. That's 1/2 CV squared. And at time 0, we know exactly what those voltages are. That's a given piece of information for this problem. The initial energy stored in the capacitors is not that difficult to find. We know we have C1, we have V sub 1 of 0 was minus 2. So now V sub C1 of 0 is 1/2 C1 V sub 1 of 0. And this V sub 1 is squared. 1/2 CV squared. Or the energy in capacitor 1, who knows what I'm touching? Really? Do I dare do this? No. All right, so I'll just continue. Two minutes is all I have to do this. So let me quickly walk through. You know how to find the initial energy stored. Oh boy, I lost all my, I wondered what happened. All my text disappeared, all my questions. We're done. Somebody just gave us a circuit and we're looking at it. I don't know what happened. Do I do this again? This is getting a little nervous now. Okay, we are done now, I think. But we can immediately find the energy stored in A, correct? Then, what do we do? Well, what we're going to do is we're going to find the equivalent capacitance. We can combine those series capacitors into an effective capacitor. We know their initial voltage. What's the initial voltage across the two extreme terminals of that capacitor? 8. So now we know the voltage on that capacitor at time 0, the effective capacitor. We can solve that circuit to find I sub 0, doing our RC analysis. We can then step our way through finding all of that data to answer those questions that now magically reappeared so that you can work on them later. But eventually those two capacitors will have charge on those, one on C1, one on C2, where if you looked at the combination from the two terminals of those two series capacitors, the resistor sees nothing at infinity. It's now the effective capacitor has now given off its energy, but you still have some charge left on these two. Why is that? Well, if you look at the effective capacitor here, it's 4. When you series combine 5 and 20. So now the effective capacitor is smaller, but you had more capacitance to begin with. That difference is now the reason why you have some stored energy or trapped energy in the circuit. We'll pick up with step responses tomorrow.